Welcome to session 2, which will talk about networking fundamentals. Further to our earlier discussion on computer networks, let us now look at some of the fundamental concepts that underpin networks. In this session, we'll look at, or we'll try to explain bandwidth, the difference between bandwidth and throughput. We'll talk about the OSI model, the layers of the OSI model, intranets and extranets. We'll cover a few key topics that are network terminology, bandwidth, network models, and so on. The recommended tests are shown on the screen, on the slide, 3 major tests which we refer you to. Data networks developed as a result of business applications that were written for microcomputers. The microcomputers were not connected, so there was no efficient way to share data amongst them. It was not efficient or cost-effective for businesses to use floppy disks to share data. So the concept of a sneakernet emerged, where you created multiple copies of the data and someone walks around, trying to share that. Data networks developed as a result of business applications that were written for microcomputers. Floppy disks were used to share the data, which was not efficient, like I've said. 3 problems were needed to be addressed for businesses: how to avoid duplication of the equipment and resources, how to communicate efficiently, and setting up and managing a network. A very brief history: in the mid-1980s, network technologies that emerged were created with a variety of hardware and software implementations. So there was issues of incompatibility. One early solution was the creation of local area network standards. LANs provided an open set of guidelines that companies used to create network hardware and software. The insufficiency of LANs as businesses grew ushered in a new technologies such as the metropolitan area networks and wide area networks, which connected various LANs at different sites, which were geographically very dispersed. Now, equipment that connects directly to a network segment is referred to as a device. These devices are broken up into 2 classifications. There's the end-user devices, which includes computers, printers, and scanners. And then there are the network devices, which include all the devices that connect the end user together to allow them to communicate. So there are 2 classifications: end-user devices and network devices. Each network interface card is identifiable by a unique code called the media access control address. This address is used to control data communications for the host network. Right. So once you have a network interface card, you have a MAC address. Network devices are used to extend cable connections, concentrate connections, convert data formats, and manage data transfers. Examples of network devices include, repeaters, hubs, bridges, switches, routers, and so on. This diagram shows you examples of Cisco devices, how they are diagrammatically represented as. So let's look at some of these networking devices. A repeater is a network device used to regenerate a signal. Repeaters regenerate analog or digital signals that are distorted by transmission loss due to attenuation. So as you send a signal, it suffers distortion or attenuation, and therefore you need to regenerate the signal. So the repeaters are for this. They don't make any intelligent decisions apart from simply forwarding packets. Then there are hubs. Hubs concentrate connections. In other words, they take a group of hosts and allow the network to see them as a single unit. Bridges convert network data formats and perform basic data transmission management. Bridges provide connections between LANs. There could also be workgroup bridges, which add more intelligence to the data transfer management. They can determine if data should remain on a LAN or that data should be transferred to a different connection. Routers, on the other hand, are intelligent devices. Unlike repeaters, they can regenerate signals, concentrate them, concentrate multiple connections, convert the data transmission formats. They manage the data transfers. They can also connect a WAN, which allows them to connect LANs that are separate by great distances. So routers are very, very important networking devices. They are called layer 3 devices. Let's talk about network topology. A topology defines the structure of the network. One part of the topology definition is a physical topology, which is the actual layout of the wire and the media, or the media. The other definition is about the logical topology, which defines how the host accesses the media to send data. So there are two definitions of topology: physical topology and network and logical topology. Physical topology talks about the actual layout of the wire or the media, and the logical topology talks about defines how the host access the media to send data. A number of physical topologies are used. The most common are the bus topology, which uses a single backbone cable that is terminated at both ends. In those days, if you're using a bus network and you didn't have the terminators, it would not work, because you needed to put these terminators at the end. So you always see network engineers, guiding and looking out for these terminators. And it's an important, if your network is not working, the first thing you look out for is a termination there. And if someone wanted to sabotage your network, then they go and remove the terminator from it. So in this bus topology, all the hosts connect directly to this bus. Then there's a ring topology, which connects one host to the next and the last host to the first, so in the form of a ring. This creates a physical ring of a cable. Then you also have the star topology, which connects all cables to a central point. You can also have an extended star topology, which links individual stars together by connecting the hubs or switches. You can also have a hierarchical topology, which is similar to like an extended star. However, instead of linking the hubs or switches together, the system is linked to a computer that controls the traffic on the topology. So it's like, a star. The main difference is that at the central point there, you use a computer that connects the various parts together. Then we also have the mesh topology, and it's implemented to provide as much protection as possible from interaction. So you have every host connecting to every other host on the network. So there are multiple connections. Now, you can then see that there are various paths from one computer to the other. So we've talked about physical topology, right? We've talked about the various types of physical topologies. Now, let's talk about the logical topology, which is how the networks, which determines how the hosts actually communicate across the medium. There are two common types of logical topologies. There's a broadcast topology and a token person. Broadcast topology indicates that each host sends its data to all other hosts on the medium. So you broadcast it. You just shout it out. And everybody on the network can hear you. So you are broadcasting. Then there's token person. In token person topology, there's something like an electronic token, a code. It's passed sequentially to each host. So you don't broadcast the information, but you pass it to one another. So whatever information needs to be passed on, you pass it to the next person. The person examines it. If it's meant for me, then they keep it. If it's not, then they pass it on. So when a host receives a token, that host can send data on the network. So instead of broadcasting, everybody shouting, you get a chance to send. Now, think about the advantages of both broadcasting and token. In broadcasting, everybody can shout at any time or send their information at any time. In token, you only send information when you have the token. So the token gives the right to send information. The two types of networks that use token person are token ring and the fiber distributed data interface, the FDDI. Let's turn our attention to explaining what protocols are and their importance. Protocol suites are collections of protocols, and protocols are rules that enable a network to communicate between hosts, or enable communication between hosts to take place. So a protocol is a formal description of a set of rules and conventions that govern a particular aspect of how devices on a network communicate. Protocols will control all aspects of data communication: how the physical network is built, how computers connect to the network, how data is formatted for transmission, how the data is sent, how computers connect to the network, and how to deal with errors. These network rules are created and maintained by many different organizations and committees. So these protocols are created and maintained by many different organizations. There's the IEEE, there's the ANSI, there's the TIA, there's the EIA. Without protocols, computers cannot make or rebuild the stream of incoming bits from a computer, onto its original format. So protocols are key to what? The communication. Now, local area networks. Local area networks will normally consist of the following components: computers, network interface cards, peripheral devices, networking media, and network devices. LANs allow business to locally share data files or computer files and printers effectively. So if you have a LAN, you can have one single printer and everybody can make use of it. Some common LAN technologies are Ethernet, token ring, and FDDI. Wide area networks, or WANs, they interconnect LANs, which then provide access to computers or files in several other locations. WANs allow computers, printers, and other devices on a LAN to be shared at distant locations. They are designed to do a number of things: operate over large and geographically separated areas, allow users to have real-time communication capabilities with other users, provide full-time remote resources connected to the local services. Some common technologies used for WANs include modems. And we said a modem is what? A modulator, demodulator, which allows you to connect to a telephone wire. Yeah. There's a ISDN, there's a DSL, there's a ATM frame relay, SONET, and so on and so forth. So these are all technologies that are what? Used in order to what? Build WANs. If you want to build a LAN, you don't necessarily need a modem. We saw the technology used for building LANs, but for a WAN, then you need different technologies or different types of technology. And each of these technologies I've mentioned have its own advantages and disadvantages. Metropolitan area networks, or MANs. Wireless bridge technology that sends signals across public areas can also be used to create what? MANs. A MAN usually consists of 2 or more LANs in a common geographic area. Typically, a service provider is used to connect 2 or more LAN sites using private communication lines or optical services. An example is a bank with multiple branches, which may utilize a MAN for, so if you take Accra, for example, GCB would have several branches in Accra. So it's a metropolitan area network that will build around here in Accra. Storage area network is a dedicated high-performance network used to move data between servers and storage resources. So here the focus is on data, the movement of data. So storage area networks technology allows high-speed server to storage, storage to server, and server to storage, storage to storage, or server to server connectivity. This method uses separate network infrastructure that relieves any problems associated with the existing network. So it's got its own infrastructure, separate from the current ones. There are a number of features, or features that are unique to this. There's performance. They allow concurrent access of disk space or tape arrays. Availability. The SANs have a built-in disaster tolerance. The data can be duplicated on a SAN up to 10 kilometers away. Scalability, a SAN can use a variety of technologies. This allows easy relocation of backup data, operations, file migration, and data replication between systems. There's the virtual networks or virtual private networks or VPNs. It's a private network that is constructed within a public network. We've talked about this, or you'll come across this in your course on information security. Yeah? So it is a private network that is connected within a public network infrastructure, such as the internet. A VPN is a service that offers secure, reliable connectivity over a shared public infrastructure. They are the most common and most cost-effective method of establishing a point-to-point connection between remote users. This works by creating a tunnel, a secure tunnel between the two computers. So you have the internet, and then over that internet, you build a private tunnel, or an encrypted tunnel, over which your communication will pass. There are a number of types of VPNs. There's access VPNs, which provide remote access from mobile and small office, home office, users to an intranet or extranet over a shared infrastructure. Access networks VPNs use analog, dial-up, ISDN, DSL, mobile IP, cable technologies to securely connect mobile users, telecommuters, and branch offices. There's an intranet VPNs. They use dedicated connections to link regional and remote offices to an internal network over a shared infrastructure. Of course, then there's the extranet VPNs, which use dedicated connections to link business partners to an internal network over a shared infrastructure. One common configuration of a LAN is an intranet. Intranets are designed to permit users who have access privileges to the internal LAN of the organization. So if you take University of Ghana, for example, we have an intranet. If you're not at this end, you cannot use those certain resources within that intranet. Within an intranet, you can install web servers, Extranets refers to applications and services that are internet-based and use extended secure access to external users or enterprises. These are accomplished normally through passwords, user IDs, and other application-level security. Let us now look at bandwidth and explain why bandwidth is important. Bandwidth is defined as the amount of information that can flow through a network connection in any given period of time. Bandwidth is finite and demands increases constantly, so people are always looking for more bandwidth. For one connections, it is usually necessary to buy bandwidth from a service provider. Bandwidth is an important factor that is used to measure network performance and network design, and is key to understanding the internet. The delivery of rich media content, such as streaming video and audio over a network, requires tremendous amounts of bandwidth. So to watch this video, for example, the amount of bandwidth you'll be consuming will be very, very high. A successful networking professional must anticipate the need for increased bandwidth and act accordingly. So you are designing a network for a company, think ahead. How much bandwidth will they be requiring? There are two analogies to the issue of bandwidth that you can use to visualize. Think of it as the width of a pipe or as the number of lanes on a highway. If you think of it as a width of a pipe that delivers water, then the width of the pipe that delivers water to a city will be much larger than the one that delivers water to your house. So the larger the width of the pipe, the more water that it can deliver. If you think of it as a number of lanes on a highway, then the more lanes you have, the more information that can flow, the more cars that can flow. How do you measure bandwidth? In digital systems, the basic unit of bandwidth is its bits per second. We measure bandwidth in bits per second. Bandwidth is a measure of how many bits of information can flow from one place to another in a given amount of time. The table shows you some other units that are used. So bits per second, kilobits per second, megabits per second, gigabits per second, and so on. What are some of the limitations of bandwidth? Bandwidth varies depending upon the type of media that is, as well as the LAN or WAN technologies that we are using. So, for example, signals will travel through twisted pair copper wire, coaxial cable, optical fiber, and air, differently. The actual bandwidth of a network is determined by a combination of what? The physical media and the technologies chosen for signaling and detecting network signals. So there are two things that determine the actual bandwidth, or a combination of things, the physical media and the technologies that you choose. You might note, for example, that you might get a service from Vodafone or MTN, and they will tell you we are giving you what? 8 megabits per second. But when you check or you try to access it, you see that you are really not getting 8 megabits per second. You are getting maybe, say, 4 gigabits or 5.6 megabits per second. That is what you're actually delivering. And this is because of the other factors that, under ideal conditions, yes, you may get the 8 megabits per second, but in reality, you're only limited to what? The 4. Now, throughput. Bandwidth is a measure of the amount of information that can move through the network in a given amount of time. Therefore, the amount of available bandwidth is a critical part of the specification of a network. We've said that a typical LAN might be built to provide, let's say, 100 megabits per second to every desktop user. But this does not mean that each user actually gets this. The user might get something less. And this will be true under ideal conditions. So what you actually get is the throughput. And this is the example I was talking about. So the throughput refers to the actual measured bandwidth at a specific time of day using specific internet routes. So throughput and bandwidth, though similar, one measures the actual and the other refers to what? What you get under ideal conditions. In most instances, the throughput is far less than what has been advertised. There are a number of factors that determine throughput. The internetworking devices, the type of data being transferred, the network topology, the number of users on the network, user computers, the server computer, and the power conditions. It is important to know the theoretical limit of the bandwidth because the actual one will never be greater than this theoretical limit. So as a network engineer or designer, you have to take that into consideration. Okay, this is the theoretical limit. So once you know what the theoretical limit is, then you can then design your system accordingly, taking that into consideration. Right, how do you do your data transfers? Network designers and administrators are often called upon to make decisions regarding this bandwidth. One decision might be whether the current LAN backbone is, for example, has sufficient bandwidth for streaming a video training program. So in doing this, the people working behind the scenes, in these video sessions, for example, the people working behind the scenes will determine, okay, do we have enough bandwidth to stream these videos, for example, live? There's a simple data transfer calculation that could help to make such a decision. And the formula is shown there. It is the formula for transfer time is the size of the file divided by the bandwidth. This will allow the network administrator to estimate several of the important components of the network performance. The unit of measurement of this is critical. If the bandwidth is measured in megabits per second, the file size must also be in what? Megabits, not in megabytes. You can see the difference there, which I'll point out to you. One of them, the B is what? A small b. Yeah? A B is a small b. The other one is a capital B. Megabits and megabytes. The byte is a capital B. The bit is a small b. Note that when you are... yes. There are two things to estimate. That the result you get here is just an estimate. and it's also a best case. It's a best case. The data transfer calculation is a simple one, and one must be careful to use the same units, like I'm saying. Something to think about. So you try to answer this question using the formula that we came across as T equals to S divided by the size of the file divided by the bandwidth. Be sure that you have the units correctly. Yeah? Would it take less time to send the contents of a floppy disk full of data, that is 1.44 megabytes, over an ISDN line, which has 122 kilobits per second, or to send the contents of a 10 gigabyte hard drive full of data over an OC48 line, which has a capacity of 2.4 gigabits per second? So which will be faster? Let me turn my attention now to analog and digital signals. Radio, television, and telephone transmissions have, until recently, been sent through air and over wires using electromagnetic waves. Analog bandwidth is measured by how much of the electromagnetic spectrum is occupied by each signal. The basic unit of analog bandwidth is a hertz, or cycles per second. The units of measurement that are commonly seen are kilohertz, megahertz, and gigahertz. These are the units used to describe the frequency of cordless telephones, which usually operate at either 900 megahertz or 2.4 gigahertz. At what frequency does your mobile phone operate? Do you know? In digital signaling, all information is sent as bits, regardless of the kind of information that it is. Voice, video, and data all become streams of bits, and when they are prepared for transmission over digital media. This type of transmission gives digital bandwidth an important advantage over analog bandwidth. What are the advantages of digital transmission? Let us now discuss networking models. The concept of layers will be used to describe communication from one computer to another. It will explain how computer networks distribute information from source to destination. Invariably, we'll be talking about the TCP/IP model. The information that travels on a network is generally referred to as data or a packet. A packet is a logically grouped unit of information that moves between computer systems. As the data passes between layers, each layer adds additional information that enables effective communication with the corresponding layer on the other computer. The OSI model, to address the problem of network incompatibility, I said earlier on that there were several standards or several companies that they were all doing different things. So to address the problem of network compatibility, the International Organization for Standards, ISO, researched networking models like the ones that were proposed by the Digital Equipment Corporation, Systems Network Architecture, and the TCP/IP. The idea was to find a generally applicable set of rules for all networks. So they came up with the Open Systems Interconnection, the OSI. So as a descriptive model that the ISO created. Now don't confuse these two, OSI and ISO. One of them is an international standards organization, and the other is the Open System Interconnection. They divided the communication under the OSI model. Communication was divided into a number of layers: application layer, presentation layer, session layer, transport layer, network layer, data link layer, and then a physical layer. In order for data to travel from the source to the destination, each layer of the OSI model at the source must communicate with its peer at the destination. So there's a sort of peer-to-peer communication. During this process, the protocols of each layer exchange information, which is called the what? Protocol data units. Data packets on a network originate at a source and then travel to what? A destination. In doing this, the data is transferred from, say, layer 7, through 4, 7, layer 7 through 6, 5, and then 4. Layer 4 adds more information. You know, this grouping of data the layer 4 does is called a PDU segment. TCP/IP was developed as an open standard. This meant that, so we've looked at the what? the OSI model, and then we want to look at the TCP/IP reference model. This was an open standard. This meant that anyone was free to use a TCP/IP. This helped to speed up its development. You know, unlike the OSI that had 7 layers, the TCP/IP had 4 layers. You know, note that even though some of the names may be similar, they are not the same, exactly the same. The TCP/IP has an application layer, transport layer, internet layer, and then a network access layer. In the TCP/IP model, the application layer handles issues of representation, encoding, and dialog control, e.g. file transfer protocol. There's FTP. I don't know how many of you have used FTP before, but there's a protocol known as a FTP that you can use to transfer files. The transport layer deals with the quality of the service issues of reliability, flow control, error correction, and so this is done by the transport control protocol. The purpose of the internet layer is to divide the TCP segments into packets and send them from any network. So that is the internet protocol. The network access layer is concerned with all of the components, both physical and logical, that are required to make a physical link. It includes the networking technology details, including all the details in the OSI physical and data link layers. So the network access layer actually combines the 2 layers of the OSI model, the physical and the data link layers. It combines them into one. This brings us to the end of the session.